66 million years ago, a rock 10 kilometers across hit Earth at 20 kilometers per second. In 1 second, it released more energy than all nuclear weapons ever built. This is the story of the impact that ended the age of dinosaurs, told in honest numbers you can actually picture. Stop and guess before we give the answer. The Hiroshima bomb released 15 kilotons. 1 teraton is a trillion tons of TNT. Chicxulub released 100 teratons. Do the math in your head while we lay out the evidence. 66 million years ago is not a hazy date. It is pinned by the iridium layer found in rocks worldwide. That thin band of metal from the asteroid is the exact same age as the crater, and it marks the boundary between the Cretaceous and the Paleogene. The impact did not just kill dinosaurs, it reset the entire biosphere. 100 teratons, write that down. It is billions of times the energy of Hiroshima. To picture it, the blast generated tsunamis hundreds of meters high, threw debris into orbit, and ignited global firestorms. The dust and sulfur blocked sunlight for years, turning Earth into a cold, dark world. Nothing larger than 25 kilograms survived. You have probably walked over parts of the crater without knowing it. The city of Merida sits near its outer rim. The entire ring structure is visible only from orbit or through gravity surveys. Impact melt rocks drilled from the peak ring contain shocked quartz and even traces of the asteroid itself. That is how we know it was a carbonaceous chondrite, not a comet. Here is the size difference on a log scale. The Chicxulub impactor was about 5 kilometers in radius, or 10 kilometers across. The Chelyabinsk meteor that exploded over Russia in 2013 was only 9 meters in radius, barely a blip. That factor of 500 in size means a factor of 125 million in volume, which translates to roughly a factor of 200 million in energy. That is why Chelyabinsk injured people, but Chicxulub ended a geological era. Now zoom out from the Yucatan crater, past the whole Earth, and out into the solar system. The asteroid that hit was 10 kilometers across. Against the Earth it looks like a speck. Against the Sun it is microscopic. That speck hit with the force of 100 teratons because it was moving at escape velocity, 20 kilometers per second. Kinetic energy goes as velocity squared, and Earth's gravity well gave the rock an enormous head start. So how common are Chicxulub-scale impacts? The impact record on the Moon, Mercury, and Mars tells us the rate. Objects 10 kilometers or larger hit the inner solar system roughly once every 100 million years. That means you are not overdue. The last one was 66 million years ago, and the next one is likely tens of millions of years in the future. The chance that one occurs in your lifetime is effectively zero. Check your mental math. Pause the video and commit to an answer before we reveal it. Answer C, 200 million times. 100 teratons is 100 billion kilotons, divided by Chelyabinsk's 500 kilotons, that is 200 million. Chicxulub's energy dwarfs anything humans have ever produced, and that is exactly why it reshaped the entire planet. The rarity of such events is our best reassurance. First, the raw numbers, 100 teratons. That is the energy that ended the Cretaceous, and it came from a rock only 10 kilometers across. Second, we have physical evidence. Drilling into the peak ring retrieved shocked minerals and melt rock that confirm the impact scenario down to the mineral level. Third, the rate. A Chicxulub scale hit is an extremely rare event with an average waiting time far longer than human history. The solar system is not aiming at us. Next time, we will step back and chart every impact size against its frequency. You will learn why we see a Chelyabinsk every few decades, but a Chicxulub only once in 100 million years, and how that curve shapes our planetary defense priorities.